Thanks for coming to the session. My name is Brad, and I'll be talking about GFXReconstruct, which is a tool suite for capturing and replaying essentially Vulkan calls. We have a copy of our slides on our website, but of course they're up on the XDC site as well. I'm going to go through a brief overview of what this thing is, talk about what the use cases are, and why you'd want it. I'll go through how you capture, replay, and use other tools on streams. I'll go out a little bit into the architecture depending on how tired people look and how hungry they look, and then try and do a live demo. But first, and I realize I won't be seeing hands up from YouTube, but how many people have actually used GFXReconstruct here? That's okay, that's not bad. How many of you have used it just from the SDK, the Vulkan SDK? How many people built it from source? Okay. That's a lot. Okay. That's probably about half the, third to half the people. Okay. So some people are going to know what this is and some people aren't. The source code is available on GitHub, so you can go and take a look at it now or whenever you'd like. But the fundamental thing is it captures Vulkan commands to a file and then allows you to replay them. The source base is in C++ with some Python generators, since we use the Vulkan XML to generate encoders and decoders and the things that actually replay the commands. Runs on Linux, Android, and Windows. It's designed to be API agnostic, so the idea is that it could do OpenGL, could do OpenXR, but right now what we have is Vulkan. And then there's a handful of additional tools as well as capture and replay. There's a lot of different use cases. The one that we see the most is regression testing. So people will take a capture of an application or a game, and what we store is all the Vulkan calls essentially verbatim, and then replay them as closely as they can be replayed, which is not always possible, but we try to do the best we can. Other reasons you might use it are for bringing up silicon, which includes architecture simulation, bring up the first passes of things in FPGA or whatever. And finally, for bug reporting. So if somebody wants to run a game and they know there's an issue on a driver with a particular Vulkan call or a series of calls, what you can do is just take a capture and then send that to the platform vendor or whatever to take a look at. So we provide this thing in a Vulkan API layer. How many people are familiar with the way the loader works on Vulkan? Okay, I'll just mention then that the Vulkan loader does this work of bringing in shared objects to hook basically between applications and the driver. And we use that facility to basically just catch all the Vulkan calls in core 1.3 and many useful extensions, but not all of them because there's a lot of them. We capture most inputs and outputs with a particular exception. If the function call returns an error, then we don't store outputs because those outputs would be invalid. And we also don't store some inputs that are also outputs. So you may be familiar with the two-call idiom, where the first call is you find out how much space you need, and then the second one is you actually make that call to get that data. We don't store the inputs. We only store the outputs from the driver. An example is enumerate device extension properties, where you pass in the number of extension properties that you first ask how many, and then you allocate the size of the extension properties structures, and then you pass those in. I was afraid of this. I'm getting warm up here. Someone take this off. So probably the easiest way to use GFXReconstruct is through the Vulkan configurator, vkconfig, which is a GUI tool. And I'm going to ask more questions. How many people have used vkconfig to do capture? Oh boy. Okay. So how many people then are using the instance layers environment variable to do it? Huh. All right. So, and then how many people use the actual command line tool, gfxrecon.py? Not a lot. Okay, so most people, you're all interacting with it through the instance layers and the environment variable. That's interesting. That's the way I do it, but I assume that's because I'm not very good with UI applications. Okay, great. So if you're going to capture, there's a couple of options that we offer. A Vulkan application can map memory, write what they want into that memory, and then unmap it. And that's the way you provide textures and vertex buffers and other data. But you can also map it and then just not let it go. So if an application does that, we need to track what's changed and store that in the capture file. So by default, we mark pages read-only and then detect through a signal handler when those have been changed and write those out. That's the default. You can turn that off. We've had cases where some applications and engines interfere or delete our signal handler. So if that's the case, you can use assisted mode if an application uses flush mapped memory ranges, which not everybody does, or just fall back on unassisted. And so that means that every time there's a draw call, we just write all buffers all the time to make sure we get any changes that were made. But that's frequently impractically slow. We also support trimming. So you don't want to have to capture all of an application or a game and then replay all those frames. You'd rather just play back the frames where there's an issue that you want to review or something that you want to run for regression. So we can capture multiple frame ranges or use a hotkey on desktop systems. On Android, we don't support that yet. All graphics state up to the range that's being captured is tracked. And then when we begin the trimmed range, there may be several, the tracked state is stored in the capture file. So in this example here, I want to trim to frames 1, 2, and then 10 through 20. So I'll get 3 files for that. And each one will have state set up for each of those ranges, all the way to 1, all the way to 2, all the way to 10 to 20. We are a little bit conservative. We don't know what future frames might reference. So we end up storing in the capture file everything that exists up to that point. We do have a tool for optimizing away those things, and I'll describe that a little bit later in the slides. Okay, you have a capture, you want to replay it. We do attempt to replay as close to the original as possible. The one thing that these systems have these days is you can have embedded, of course, a GPU and the discrete GPU in your laptop, or you can have a system with multiple GPUs. And so if you capture a stream, you get it on the GPU that was chosen by the application. So to replay it, you can provide --GPU, which uses the index, I believe, that comes out of enumerate devices. And that way you can choose exactly which GPU to replay on. You can replay on a different driver version or a GPU model or even a GPU family, but these are all tricky because an application, especially in Vulkan, chooses extensions and settings which are very specific to the GPU, more than it would have ever been in OpenGL. So we support a couple of ways to help with that. The primary one is to do memory translation. Memory translation. So the two most important ones, I've got 3 written down here, but the 2 big ones are remap and rebind. So for remap, we take all of the memory types that were captured and try and find mappings to those for the memory types in replay. And then when a memory is allocated, we just change the mapping type, which is pretty high performance, but may not be very accurate, which is to say it might crash. So, or just give you wrong data. Rebind is the more interesting option to use. It defers all allocations until that memory is used, and then uses Vulkan memory allocator in order to reallocate with the right alignments and the right settings and the right types. But that means their performance might be a little bit slower. This is kind of my private favorite option, this remove unsupported. When you create an instance in capture, you provide a list of extensions. So in replay, normally we just pass that list of extensions through, but driver versions change the number of extensions available. Some go away. An example was VKKHR ray tracing was a provisional extension for a while, and it was split into 3 different ones. So we have some captures in our CI system that ask for this extension, but then don't use it. And so in order for us to replay it, we use remove unsupported command line option, and that goes and removes any extensions from the instance creation that don't already exist on this replay device. Of course, if an application uses the extension, all bets are off. We do warn if in replay a function returns a different return code than it did in capture. That's usually an indication that something's potentially wrong, But often it could just be like an event hasn't returned yet, or something returned at a slightly different value, which is still valid. In the case that a captured application made allocations that failed, then in replay, we'll try and make those allocations too, and sometimes they succeed. And so what that means is that the memory access pattern changes on replay. So to prevent that, you can provide skip failed allocations, or SFA for short. And that means that anytime an allocation was made in capture that failed, we just don't do that on replay. On Android, we only make one surface. So for a capture that was created that opened multiple surfaces, you can choose the index directly. You can save off screenshots, all of them, or some range. An interesting feature that was merged recently is virtual swap chain. So you may not know that swap chain acquisition index order might change even on the same GPU and the same driver if you're using mailbox or immediate present mode. So when the application is being captured, it's setting up all of its rendering state and all of the rendering targets using these handles. But those are not necessarily linked to the index that's returned from acquire. So when you do the replay, it may actually just render the wrong thing because we're filling up all the data and rendering into render target and then acquiring something different and presenting that to the screen. So virtual swap chain virtualizes that access. And in fact, we discovered, and I think this is right, but someone can correct me if they know it's wrong, Android 12 and 13 potentially change the number of swap chain images that are returned. So then all bets are off there. There's nothing you can do unless you use this virtualization. And finally, although I think this is mostly just used by me for testing, you can even request that a replay on a different platform use that platform's Windows system interface. Like I had a Linux replay, Linux capture that I was trying to debug, and I was able to replay it on Windows. But of course, the extensions are pretty specific, and so that doesn't always work. Other tools in the suite include info, which is pretty straightforward. It just prints the number of frames in the capture, prints other information about it. Optimize, I was mentioning earlier, when we trim, we just store everything. You can run optimize on a capture and that'll produce a new capture by basically marking all of the resources that are used and then not copying over the ones that aren't used. You can change the compression format. A kind of a fun esoteric one is extract. It'll take all the shader binaries out of a capture and store them in a directory so you can look at them, or you can alter them and then replay the capture, changing the shaders in them. But that's advanced use, I think. And finally, we have a new tool. We've been working on it for a little while. It'll be in the next release called Convert, which produces JSON lines output for a capture. So every function call from Vulkan that's in a capture, we produce a detailed one per line. So it's not exactly readable, JSON record for the function. And I'll show that at the end if I can get that to work. So we have a file format and we lock it down. Recently, we've been trying to make sure we deprecate blocks and don't change things, so you can always replay old captures. And I was going to go through this slide and talk more about what those are and what those look like. But really what I wanted to say was we don't really tell people what they should do is read a file. What we tell people they should do is take one of the tools we have, which uses a consumer, and make your own copy of the consumer. And then you don't have to worry about what's in the file. You don't have to worry about the file format. You just subclass the consumer and we take care of all that for you. I'm keeping track of the time and make sure I don't dive into too much detail here, which is my trademark. The capture manager component deals with API specifics, anything which is not an actual Vulkan call. The encoder is a base class which is meant to serialize API call info and parameters, basically puts them into buffers. On the replay side, the file processor object knows how to read blocks from a file, but it doesn't know what's in those blocks. It doesn't know what's in any of the Vulkan blocks. And it knows how to decode and uncompress and then call decoder subclasses. Those decoders know how to deserialize the API call info for something like VK create image view. It knows how to pull out all the parameters for those. And it takes those parameters and calls consumers. The most obvious consumer is the Vulkan replay consumer, which takes those parameters, may mess with them, and then calls Vulkan directly. I think the directory structure is fairly straightforward. The one thing I wanted to point out is that we generate a lot of code from vk.xml, the encoders and decoders, and some of the consumer code. And we do that by hand. And the reason we do that is that we've had a couple of experiences where the structure types and the layout of the structures in the Vulkan header changed. And so if we don't keep an eye on it, what you'll do is you'll have an older version of the code which wrote one struct to disk, and then a new version which reads a different version, and so fails. The parameters are corrupted or whatever. So I'm going to give some, hopefully not too complicated, details about how we do capture and replay. So when the Vulkan loader pulls in our layer, we give it back a big table for all the Vulkan functions, which contains what functions we would like to be called. And so one of those, for an example here, is create image view. So if an application calls vk create image view, it actually calls us. Potentially, might actually call us through other layers first, and then there might be other layers downstream. This can get really complicated. But what we do in our function is potential preprocessing. Then we call down chain, and that means call the next level down, which could be a layer or a driver. Then we take the inputs and the outputs for that function, which may or may not have been successful, and encode them into a buffer. What we do with that buffer then is pass it off to the Vulkan Capture Manager to do something with it. And I've written K-mode track and K-mode write, and these are basically just bit masks that we keep track of. So the actual mode is a concatenation of all these, an OR of all these masks. But if we have track mode, that means we are not yet storing frames to disk. We're just keeping track of state. So we add that state to the state tracker. If we're actually K-mode write, that means we are writing frames to disk. We've already written all our state. And so instead what we're going to do is take the information for this function call, a header tag which says it's compressed function call block, the actual API call ID for vk create image view, and all the parameters, optionally compress it, and then we store that as a record in the capture file. So I guess I am giving more detail, but right. So on the other side, the file processor reads blocks from the file. If it finds one that's a function call block, this is also a bit mask. So this could be function call block or compressed function call block. It knows to call process function call also in file processor. And then what that does is it reads this block of data from the file, potentially decompresses it, figures out if the current decoder can support the API call that's been made, which we have just the Vulkan decoder, so the answer is yes. And then it calls the decoder to do work with that. So the final thing we do is in the Vulkan replay consumer, we actually take all this parameters from this buffer and decode the real parameters for vk create image view, which is like the device handle, the create info, the image and view that you want to use to create this composite image view, and then actually calls Vulkan with those things. And I want to mention, we don't store the actual handles that Vulkan passes back to us on capture. What we store is an incrementing index, basically a small integer, which could get bigger, I guess, in case of very large apps. But since we store there's no point in storing the handles or the memory pointers in capture because those will be different on replay. So we store identifiers instead and then remap those when we play them back. Right, got a little bit ahead of myself on the slide. So this is what does that work. Not drawn here is a lot of the stuff that I talked about earlier. There's a fair amount of complexity in here to do things like the virtual swap chain work, to remap memory. We try and keep those encapsulated in classes as much as possible, of course. And so those of you who've used GFXReconstruct have known, I think, possibly that it's been out for several years. A lot like other open source projects, you could download it and try it, but there haven't been guarantees about the file format or the version. So we're closing on 1.0. And so some tasks left to be done are to version the file format, make sure that that's the numbers documented, and that we have some clarity on backward compatibility. And of course, we accept issues and PRs on the GitHub repo. So how much time we have available to review those and do stuff with those depends a little bit on how much of the workload we have. We're a software consultancy, but we try to spend time on those. And so we're going to do a pass on identifying and tackling anything that we think really needs to be resolved for 1.0. And if you look at the issues list, there are a handful of those that are a big deal. And so I guess I'll try a demo. So we'll see if we can make this work. Okay, open on the wrong screen. So I'm running Vulkan configurator, which I think is the easiest way to do this. Yeah, and of course it's going to be really tiny on the screen. But when you run this, you get a series of configurations that you can run. These are layer configurations. The whole point of this tool is to set up layers, provide the settings for those layers, and then run your app. And so in this case, I've got frame capture. Here's my layer for GFXReconstruct. Got a bunch of settings. I'm just going to set it to capture everything that it does. I've got VK Cube set up here. And I launch it and it shows up there. Good. Okay, wait for it to run for a second. It's interesting how, depending on how you have HDMI set up, it might run slower. This is slower than I expected, but this is not about performance. This is about capturing the data. And so you can see down here, trying to do this without my glasses up close. This is the important part that's the output from this layer, which is the file name. Oh, it's probably a mistake. One thing the VK config does is it changes all the layer settings. So if you're going to mess with it, the best, if you're going to be running applications and doing something different, the best way to deal with that is to just cancel. So now I should be able to gfxrecon.py replay. The script is basically kind of like Git or other tools where you have subtools. They're actually called gfxrecon-replay in the tool chain, but you can provide a sub command here, and then we provide the capture name. And there it is. It's actually replaying all the Vulkan calls that were captured for VKCube. And it plays it till it's done. You can ask it for info. So some oops, actually pretty low. Okay. Notable bits here are the compression format is LZ4. You can actually make an uncompressed trace, but of course that's quite large. Total number of frames, 672. And then some more information like this is the data that was provided to create instance about the application. And for my next trick, I'm going to put my microphone down. I'm actually going to clone a repo that I have here. and build it, and then run the new tool to convert to ASCII and show you what that looks like. So hopefully I can do that in just a moment. If I'm lucky, I have most of the stuff in my history, so I can keep the microphone in my hand and just push up arrow. Nope, not lucky. Yeah, there it is. Okay. So and then somewhere in here, I've got a make command. It is a pretty beefy laptop, so this may not be how quickly it builds for you, but in general, it's quite fast to build on Linux, or using Gradle for Android or on Windows. And I think while that's happening, I'd like to talk about my favorite project. It takes about a minute to build that. And so many of you know that I am very interested in old technology. And so one of the more fun things I like to do is to run things where they're not supposed to run. Not done building yet. Okay. And this slide makes it sound like I know what I'm talking about, which is the really great part about it. But I've actually done some CPM work. That's how old I am. And one thing I've kind of always wanted to do was to run an old 8-bit CPU in a shader. So I've always thought that would be a little bit weird to get the output, but maybe an interesting thing would be to run like every possible combination of keystrokes or something. Okay, so now it's done building. Good. Okay, so here's my command line. Let's get this up on the screen a little bit. Stick at my crazy slide back there. Okay, so there's what I built running VKCube. So it's capturing now. Hit escape because we don't want to do 5 minutes of those. And then replay that. Maybe. Well, since you've already seen it run in replay, what I'm going to do is just convert to text and show you what that looks like. Okay, so this looks pretty horrible. It's JSON lines, which means every command is a JSON record on one line. And the reason we did that, and not just like a huge JSON record, is that these captures can be gigabytes. And when you convert them to ASCII, they're also gigabytes. And so you could easily choke a JSON parser. So instead we do it line by line. So you can do things like grep, use the Unix text processing tools or whatever you'd like, and just read it record by record. But what you can do with smaller traces is run it through JQ, which is a JSON processing tool. And so then you get something which is a little bit prettier. Yeah, there we go. We have a header which includes some information about the file. And then, of course, here's your first function, which is create instance. And I was talking to someone earlier about debugging traces, debugging Vulkan code with an ASCII dump. And so one of the examples that I have here is you want to do a bind memory. And you want to find out what happened there. So here's, now, yeah, one-handed. Is it bind image memory? Thank you. You know what? I bet I have it in my history, so I'm just going to go find it. There we go. Okay, so what you see here is this record is indexes the ordinal of the function in the capture. So it's the 50th function that was called. The name is vkbind memory, image memory. It succeeded. And the important things here that I want to point out are image and memory are these handle IDs. So these are not the original handles, but since we're inside the capture, what I can do is if I want to know more about the image that was bound here, I can search for image 23 as an output. Yeah, I'm gonna type this wrong again with my left hand now. And let regex solve some problems for me. Okay, so here's actual p image was created in this function here, which is create image. That was just a little bit earlier, index 47, and you can see it's a 16-bit depth format buffer, 500 by 500. So this is the depth format for the screen. So this is how you can sort of jump back and forth through the ASCII stream with this. Now if I could just find my mouse. Nope. Okay. So thanks. You can check out the GitHub repo for the source. And if you have any questions, you can send me an email. If you have any questions offline, but I could take them now as well.
Hello.
Hello.
So you said you have a page guard version. On Linux, do you use exception for that, or do you use mnsoft 30?
The question is, how does PageGuard work on Linux? I don't actually know the details. I know we set up a signal handler. So I think we're touching the actual, like mprotect on the page. Yeah.
Print that JSON output, kind of like the API dump layer does, or maybe it's just not just use the API dump layer.
Right. The question is, would it be better to pretty print the JSON output or do something like API dump? Because API dump, who's used API dump and looked at the output of that? Okay. So API dump produces very verbose output, which is extremely useful. We sort of tried to strike a middle ground between producing output that could be debugged and not dumping a really huge file. So we, in particular, a non-goal is replaying or from this dump. So I think what API dump gives you is really close to something you could play back. Like you could reassemble that into a file if you had a sophisticated Python script. So one thing we can do is we can turn API dump into this format for testing. We could probably do the reverse. It's not a very complicated piece of Python, so I'll take that as...
The JSON has all the same information that an API dump would have.
It's very similar. API dump outputs all the types for all the objects, which is super helpful, but that just means that the types are repeated over and over again. And so we chose in this case to not output the type because the type is very well represented in the spec and in the header. So it's missing that. And I think that might be a little difficult to go back to from this format. But the idea here was to make something that you could look through and dump out and say, oh, that's what I expect, or that's not what I expect. And so hopefully it does that, but it's fairly new. So this is an opportunity to say, this doesn't do what we want. It would really be great if it did this other thing instead. Yes. Okay. Could you repeat? Yeah. Right. The question is, do we plan to reconstruct the threading behavior as well? So, because right now I think we're single threaded, we just play back everything as it came to us. The answer is yes. It's in our roadmap. You can't make super hard schedules sometimes, but it is actually pretty high on our priority list to make separate threads and make them behave that way. As you can imagine, there's just a little bit of design that has to go into doing that right. So. Right. The statement is that perhaps before timeline semaphore, you might have gotten correct behavior no matter what you do. I'm not sure about that. But afterwards, yeah, we haven't looked at it too much, but I agree. It's a big deal.
We also have a question from online audience. This seems very useful. What's the catch?
What's the catch? This seems very useful. What's the catch? Good question. I mean, yeah, you want me to talk about what's wrong with the thing? I mean, yeah, I don't know if there's anything that jumps to mind. It is a replay of the Vulkan commands, so it doesn't include things like system calls. There are lots of cases in Vulkan where you take memory from another API and you hook it in through. Let's see, there's struct chains you can add to allocate memory to say, I'd actually like to use this Android buffer over here. And we do the best we can to say, well, we know that there was that linkage, so we'll create a dummy version of that, but we don't know anything about how that was made in the Android app. We don't catch those commands. So that's a limitation. Sort of by design, we don't catch all the other stuff that's going around the application.
Hello. So why do you use unique, like, monotonically increasing IDs for each object instead of just like dumping the pointer value? Because when I tried to do something similar in D312 API trace, a lot of overhead seems to come from taking the pointer and then looking at the monotonic ID when you could just do that on the replay side and not have the performance penalty on the capture side.
Yeah, so the question is, why do that monotonically increasing ID on capture, and then we also remap on replay, right? So I guess we could store the handles directly in the capture file. We'd still have to remap them on replay, right? But I'm going to be totally honest with you. Some of the design was by someone else who's left the company. So I usually trust his design instincts. So I'm sure there's a good reason, but I don't know what it is. So what I do know is that you can reuse a handle in Vulkan. So at any given place in the capture, if you see a handle, you don't know whether that is the same handle that you saw earlier or whether it's been deleted and recreated and you actually have a new object. So if we do the incrementing integer handles, you know it's a new thing. So there's that. Yes. So if you have all the context in between, you know it was destroyed. But if you don't have that, if you just have like pulled out pieces, then you don't have to keep track of that. That's true. So yeah, there's some design decisions which may or may not have been differently lost to the sands of time.
Whenever you have, some games like to use the GPU to compute more I don't know how the weights of the C of the move using something like feedback or something like this. And I think that small errors tend to grow with time. As in, like, let's say, okay.
Okay, so the question is about basically taking outputs of like shaders or transform feedback and then using them as inputs to another stage later, right?
I'm getting there, but yeah, okay. So,
in the context of trimming.
Is like, let's say the driver rendering checks. So we want to do some CI and verify that the game output doesn't change. So this is the context. So when we run the trace, we currently run it from the beginning to the end. So that means that actually it's multiple minutes of let's say gameplay. And if some objects, the location is dependent, like updated every frame, then small errors are found, and the position at the time while we actually take a screenshot can be very different depending on every time you would run it, you would get it at a different position. And
Every time you run like the shader to do updates of the inputs, outputs. Every time you run the trace again. Okay, so you're saying that you run the trace, you have certain values on the screen. You run the trace again, you have different values. If that was the case with GFXReconstruct, I would consider that a bug.
Okay. So in order to remove these issues, trimming is great. That would be great because then we would be able to, we would not have these compounding errors that much because then we would just have the data that
So the question is about these compounding errors. I'm not sure where those compounding errors would come from because presumably you initialize everything at the beginning of the capture. But if there was something where somehow, so the way trimming works for us is we collect up all the state, and I believe before we do a draw for the first time inside the trimmed range, we save off all the current state. So whatever was the state accumulated in capture, to that point, that's saved.
Yeah, so that's how trimming working.
Yeah.
So the rest of my question is, would it be possible to have one trace that would be having multiple, because when you trim right now, you only have one frame per trace file.
Oh, you can have multiple frames.
You can
Yeah,
now.
yeah.
Okay, so that was where
Yeah.
Okay, so you can do this, and so that would be a way to remove the
Well, you can, well, I mean, you can do this much. You can say like frame, you know, like you want frame 100 through 200, and then you want frames 200 through 300, and it'll produce two capture files that represent those.
I don't want to capture because then you need to reapply the textures multiple times. So it's slow.
Yeah, I'm not sure quite the way around that, really. I mean, like, you want something where a single file capture can replay and draw only frames 100 to 200, and then only frames 300 to 400.
Let's say like frame 10, then frame 33, then frame 44, and if they also textures or handles or whatever can keep in between, that would be great.
I think we should probably talk about that offline. I'm not sure that that would be that difficult given the way we do things in the capture file, but I'm not sure I understand the use case, so we should probably talk about it offline.
Absolutely, yeah, I've been confusing.
Hello again. I just had a look at the code, and yeah, it just seems to be like a typical segfault handler.
Yeah.
Is there anything preventing you from using MM-Soft30? Because when I did it for DB Velvet Capture, which obviously goes through wine, whatever, we needed like a flag. We needed an extra kernel function to be able to reset the mappings. Is that what is preventing you as well from using MM-Soft30? Because the performance uplift from capture from using that as opposed to cycle handling was pretty extreme.
So right, the question is reaching technical detail that's beyond my limit. So, which is about how you do the protection on pages for PageGuard. So again, something we can talk about offline. Our performance during capture is relatively good. So that is right now, performance in capture is not an urgent thing that we're trying to address, but we can always take suggestions. So we actually have a lot of work going on right now, especially in terms of Android and getting PageGuard approved. So we should talk offline. Yeah.
As far as I know, it's possible to just replay a specific frame. But is it possible to replay the capture up to a certain command?
No. The question is, can you replay up to a certain command? The answer is not yet. So, so far the design has been pretty heavily based on frame trimming, but it is in our list. The higher priority item is to do at least 2 queue submissions, and then maybe draw after that. But yeah, I know that that's a big deal too. It's just, you know, more state has to be tracked. Oh. Any more online or any more questions? Great. No one wants to talk about what would have happened if the Atari 2600 had a Z80 in it? No? Okay. Great. Thank you very much.